The bottom.
Bottom goes to 1. Why? Both liquids, standard conditions. We just get rid of those things. Okay, so what's going to happen? So say I take, say I make X mole, or M. Let's do M. I make M moles of that. How many moles of protons am I going to make? M, right? And so we can substitute in the concentrations right here. Okay, EQ at equilibrium. So these problems, and then you can do all your math to figure out what's going on at equilibrium, right? So one of these types of questions is fair game. Just like the Pyridine question. Now, this is the hardest type of questions we have on the exam, right? So, study it. This is just like Haber reaction, right? It's just like any reaction we've written. Don't let the whole pH thing and water get you all goofed up. This could be, liquid hydrogen and liquid nitrogen go to ammonia, something like that. Same reaction quotient, same simplification. So how do we calculate the pH? We get all done with this. What does the pH equal?
Negative log of the hydrogen.
Negative log H plus. It's that easy. So KEQ, 1 times 10 to the minus 9 equals what in this? M squared. Can you solve for M? I hope so, right? Take square root. Drop it right in there. Take the negative log. You're all set. Yeah, so these problems, there's a lot of things going on, right? And I can make it easier or harder depending on what the reaction quotient is. But you practiced it once on the homework. I know that you're pressed for time on the exam, so I'm not going to make it super nasty, tricky, but know your way around, right? I might give you the proton concentration and ask you to calculate the pH. That's easy. Yes?
Liquids are the only things that cancel out in the equation, or solids?
Liquids or solids, right? And you think of it. What's the concentration of water? I know what it is. It's 55 moles per liter. But, what's the concentration of sodium chloride salt? That's hard to define. So if we put in 0.2 moles here, we know the concentration of this guy. So this is not 1 anymore. Sorry about that. If I tell you I drop in 0.2 moles, we just put in 0.2 down there. If I tell you what the concentration is, don't make it 1, But if I don't tell you what the concentration is, and it's a liquid, you can bet that it's going to be 1. Or if it's some product, you're going to need to figure it out, right? Yes?
Do we need to put 3 in front of H plus because that's not balanced?
Well, I put what?
3 in front of the H plus because
Oh.
the equation is not balanced.
Yeah, so to get this equation to balance, I actually have to add H2O liquid on the other side. That's how I balance this reaction. Because that's how acids work, right? It's going to let go of a proton. So I know I get these two things, and I just have to bring the liquid water over to balance it. So you need to be a little bit savvy sometimes how to balance it. But this is just a special case for aqueous reactions. One sec. Is everyone comfortable with this acid-base stuff? If you're not, let me know and we'll talk about it more. But practice on the homework. There's an acid-base question, a couple of them in the notes, and so work through it. Yeah?
For the reaction quotient of partial pressures, is it just products over reactants, like whatever the partial pressure is?
Yeah, so why do we do that? So what's the reaction quotient for that reaction? Same thing, right? Products over reactants. So let's do it for real. Is this thing balanced?
Yes.
I think so. They're all gases. What's the reaction quotient for this?
Concentration of ammonia gas squared over concentration of hydrogen cubed concentration of nitrogen.
Great. Okay. So if my pressure P of NH3 is 0.5, P of H2, 0.1, P of N2, 0.2, the partial pressures, remember the partial pressure of a gas corresponds to its concentration. You can figure that out through the ideal gas law, all of that stuff. And so I just substitute in 0.5, 0.1, 0.2. Just don't put products over reactants and say, it's good, I'm just going to multiply stuff out, because you're going to forget these things. Remember, the reaction quotient has the stoichiometric coefficients as exponents on the concentrations. And if you don't write out the reaction quotient for this thing, you're just going to say, oh, I know what 0.5 is divided by 0.1 times 0.2. No problem. You plug it in, you forget the exponents, you get a couple points off. But if you write out the reaction quotient and substitute in, you're all set. What's the difference between reaction quotient and KEQ?
Q's at equilibrium. And
Which one's at equilibrium?
KEQ.
KEQ is at equilibrium, and what's Q? Anytime. You know, anytime we have set of concentrations, we can calculate Q. No problem. But KEQ is only at equilibrium. So if I tell you if a reaction is not at equilibrium, you know, that will describe a different situation. Or if I tell you it's at equilibrium, give you an equilibrium constant, that allows you to solve for the concentrations. I saw a hand go up. Yeah?
Does KEQ go 1 times 10 to the negative 9?
It depends. I mean, KEQ can go from 10 to the 300 to 10 to the minus 300. What does KEQ depend on?
Van der Waals forces.
Well, what reaction you're doing. You know, KEQ changes for every reaction, for temperature, for all sorts of stuff. KEQ always changes. Now, if the equilibrium constant is 1 times 10 to the minus 9. What does this equilibrium constant tell us? How many products are we forming under these conditions? Very few, right? What's the delta G going to be for that equilibrium constant? High. High positive number, right? Delta G is high for low KEQ. How do we know that mathematically? Do we have a relationship that relates delta G and K? Delta G equals delta G 0 minus RT ln K? Is it minus or plus? I can't remember.
Well,
Is plus? So we can work it out from this mathematical relationship. That's what this tells us. Yeah?
Where did the 1 times 10 to the negative 9 come from for the last problem?
Oh, we just look it up in a table. Yeah. So if KEQ is 300, what does this tell us?
G's negative.
Delta G is negative, right? Are we forming lots of products under these conditions? Yeah, right? This concentration is high, these things are low. So KEQ can tell us, here's a good table right here. For those of you that check out the notes in your spare time, which I know is for all of you. Here's a little table right here. So on lecture 9, slide 16, it gives you a generic relationship between KEQ and delta G. So when delta G is high, is this thermodynamically favorable? No, thermodynamically unfavorable. So you're not going to have lots of products formed, right? These are really low numbers. You have to do some calculations here, but if the delta G is highly negative, you told me on the first exam, negative delta G means it's thermodynamically favorable, and we're going to form lots of products, or the reaction is going to go to completion. We're going to get mostly products under those conditions. Are you cool with the relationship between K and delta G? It's an important one. Let me see if we can find that formula just to make sure.